Alright, so hello. This is the LED circuit I made. And basically, if I just go ahead and start the simulation here, we can see that the LED is sort of like a wave pattern going through all the LEDs. And we have this potentiometer over here that's able to adjust how fast it waves through, with this all the way on the slowest end being half a second, or 500 milliseconds, and this all the way at the fastest end being zero point 0.1 seconds, or 100 milliseconds. And of course, it has adjustability all the way through. So I'm going to show you how I made this circuit by going through each step and building it from scratch. So let's go ahead and create a new Tinkercad simulation. I'll meet you there. Okay, so here we are. All we have here is an Arduino and a breadboard. What we're going to want to do is we're going to want to test one LED at a time to make sure we got the right idea. So let's just try to turn this one LED on from the 5-volt power. Connecting up the anode to 5 volts through a resistor, and then connecting the cathode to ground should allow the circuit to turn on. Let's give it a test. And perfect, we have an LED turning on. But we don't want it to always be on. We want to be able to control it. So instead, let's try to connect it to one of these digital pins. Making our way around neatly, just for now, not having to consider the factors about any of the other LEDs, just because we're testing this one right now. And we're not color coding anything, they're a little bit of a mess, but we just want to test things out. So what we're going to want to do is we're going to want to go to text code. Yes, remember we don't want to use block code just because text code gives you a bit more flexibility. And we want to check that it's connected to pin 7. So everywhere here, we're just going to change it to pin 7. And this is just the standard blink code that comes with the Arduino. And so we should see this LED blinking. And indeed, we do see that behavior. So now we know this LED works. So now we're going to wire up many more LEDs in a very similar fashion, connecting them to these digital pins. And we'll just fast forward through that, because that'll take a little bit of a while. So see you on the other side. Okay, so you just saw me wire up the entire circuit. Now we should write some code to test that out. So we'll modify this simple blinking code, and I'm going to right here create a variable, and that's going to represent the LED that we're currently testing. So it's going to replace everywhere where it says 2 with the actual test variable, so that we can change that in one spot, and it's going to update nicely across the entire code. Okay, so we can see the last one's blinking. And really the reason I'm doing this is just to make sure that every single row is connected up properly and that we have no discrepancies between where the pin is connected and which LEDs are blinking. And so far so good. We're almost at the end. This is just, okay, good, that works. So and this is the last pin, and that all works. So that's great. And now we know our circuit works and we can actually start writing the real code. Okay, so we're here in a new coding environment, and I just like this coding environment because I think it looks a little bit better and has some nice features like autocomplete. But for the most part, it's the same thing. So what we're going to be doing now is when we try to code that waving functionality. Okay, so the first thing that we're going to want to do is declare all these LEDs as an input, as an output device. So we have an array of LEDs, and this is how you declare that. And let's go ahead and start declaring our LEDs. So we have red, with at pin 3, and if we declare it's an integer. Okay. So now that we've done that, let's go ahead and add them all inside the list of LEDs. So red, green, blue, yellow, and orange. And then we'll just make a variable to store how many LEDs we have in total. And then we're going to do something, and then we're going to initiate them all, and we're going to do it in an interesting way. So we're going to do it in a for loop, and that's just to help make the code more maintainable. If you don't know what a for loop is, it's just a set of code that's going to run over a certain block of code. In this case, it's this part of code. while a certain condition is true, and it's going to do something at the end of every time it runs that. So I'll walk you through that. So this is the first thing it does. This only happens one time. It's like the setup function. It only happens when the for loop starts initially. So it's like the declaration. Then this is the condition to check. And what we're going to want to check is that I is less than or equal to 7. Because this should be 3. Because we're starting at LED number 3. Well, rather we don't have to. Okay, well, there's 2 ways to do this. So let's do it this way first. So we're starting at LED number 3, and we want to go to LED number 7, and in that LED as well. So that's why it's greater than or equal to. Another thing we want to do is this. Well, this is something we have to do. It's this is the actual increment. So I plus plus, which means at the end of the for loop, add 1 to I, and then all we have to do here is go ahead and put this to I. And what this is going to do is it's going to go from from 3 to 7 and declare all those pins as output pins. However, another way, and the way I prefer doing it, is instead of just going through this, we're going to go going through the numbers raw. We're going to go through the actual array that we've created. So if we do it this way, that's going to achieve the exact same effect. But it's going to be maintainable since we can change anything here and it's going to update accordingly. Same thing with changing anything here. And another thing we want to do is we don't want to put 5 because if we change in the feature, it's going to be hard to maintain across the program. So we can just go ahead and put that in. Okay, so now that we've declared all those as outputs, we want to do a very similar thing over here in the loop. In the loop, we want to use this blinking behavior, specifically this part. We don't want half a second delay before switching. We want no delay. But we do want a delay before an LED turns off. This tabbing is a bit off here, but it's okay. And just to make sure we got everything tabbed the same way. Although it's not necessary in C++, it's just a good, keeps things neat. And so we're going to want to change this from test. We want to go LEDs I, because that's the LED we're turning on, right? And there, and 1000 is way too long, so that's 1 whole second. And we also want to make a variable for this, so int delay. We can't use the actual word delay because that's a keyword. So we have to use something else, like for instance delay time. And then we just place that over here. Okay, so let's go and find out all the different errors we have by going ahead and compiling this code. Okay, so first thing is we just forgot to put a semicolon. Remember to put semicolons at the end of all lines. And that's it. It seems to be working fine. So there you go. You can see the waving behavior here. And so that's pretty cool. But if you recall the way the other one was working, it was actually hitting one side and then going back, right? It was not just starting again from the other side. It was actually propagating backwards. So there's many different ways we can do this. One way to do that is if we want to keep the same code here, what we can do instead is we can actually flip the entire array. Okay, so we should update the code just so both our versions match. Oops. There we go. Now both versions match each other. What we could do is we could reverse this entire array and then just go back in the loop and run the same code, and that would now be reversed. Or if you want a little bit of a less elegant solution, but this should still work, all you have to do is just put this loop again and go backwards. So in this case, we're going to start at the number of LEDs, and we're going to keep going until I is, now we have to say greater than or equal to 0. And then instead of plus plus, we're going to go minus minus. Now we're starting from the top and going down. So this should work, and then I'll show you another way in a second, which is actually keeping one single for loop just so things look a little bit cleaner. But there you go. You see it's going there, and then it's propagating back, right? Going there, propagating back. So that's one way to do it. And then right now I'm just going to show you. If you could also do something where you flip the array. So instead of doing this, you actually take the array and flip it upside down. So we can just create a function for that. All right, and here we are. We're gonna take an array as the parameter, and we'll take how long it is. Okay, so now what we're going to do is basically the way we're going to make this algorithm. So say we have our LEDs here. Those are our LEDs. We're going to start on each end, and we're going to swap 3 and 7. We're going to swap them. And then we're going to move 1 in from the front start and the end. And then we're going to swap 4 and 6. And then we're going to keep doing that until our marker that was in the beginning is larger than our marker that was at the end. And that would happen at 5, right? Because this would move on to 6, the initial marker, and the end marker would move on to 4. And at that point, we wouldn't do anything, and 5 would stay in place. So we're going to go ahead and declare those. Int start equals 0, and then int end is going to be the last index, so length of array. Okay, and then we need our for loop, and our condition is that the start is less than the end. And what are we going to do? Well, we want to swap them, but the problem is you can't. So let me show you the problem. So if we go and we say array start, right? The index, the starting index equals array end. So that was going to work. That's going to make the first, or rather our start element equal to our end element, and that's good. But now if we want to do the same thing, but we want to make end equal to the start value. The problem is that now if we try to access the start value, it's going to be the same thing as this end value because we've just gone ahead and updated it here. So what we actually need to do is we need to store this start value in some sort of temporary variable. And that's exactly what we can call it. We can call it temp. And that's actually going to store the value of start. So then when it gets updated, we still have an access to the old version of it, if that makes any sense. And let's remember our semicolons right over here. Okay, so there we go. So this should work in actually flipping the array. So let's go ahead and test the code. We'll take it over here, and let's start this. Well, of course not. No, there's always going to be certain problems. So let's go ahead and read this. Expected colon before array. So it might be that we need to put the brackets here. That might just be a syntactical thing. Okay. And there we go. That is not exactly working. So it's actually not... Oh, of course, we haven't called the function. It's only going to work if you call the function, right? So if we go over here, and we go ahead and call the function, now things should work. So we're going to start it. Oh yes, we have to pass the parameters as well. So LEDs, and so this is why I like working with the other editor. It's not going to autofill anything for me. It just makes things a little bit harder. So let's try this. So that's not giving us exactly what we wanted. In fact, oh, right. So remember how an array starts at 0? You can't, and the number of elements in the array is going to be the index plus 1. Since it starts at 0, it doesn't start at 1. And how we count things does start at 1. So we just have to do a subtraction of 1 over here. Stop the simulation first. And now will we get it? No, we still are not getting it. So a useful thing to do is debugging. And the way that works is you are able to go and pause on each line and figure out what's happening. Okay, so if I just go ahead and we'll just stop on all these lines. And we'll start this. And now that function has been called, so we're going to come in. We can also hover over things to look at their values. So this is only telling us the first value of array. For some reason, that's just how it is. So start is 0, and so now that becomes 4. And so now we can walk through this part of the code. Start is less than end, so it's going to enter this. So we're going to run this again. It's going to come here. So now if we look at array, there you go. The beginning has become 7. Run it again. The beginning is still always going to be... Oh, we forgot to increment them. That's what it is, right? So at the end of this, you need to increment the start and end. Otherwise, so you're going to keep flipping forever. And that's what was happening. Did you notice how nothing was happening with the LEDs? That's because it was in an infinite loop. It was never going to exit this while statement, since that condition would never be true. Since start and end were never changing, and since their values were met the condition in the beginning, it was going to do that forever. Alright, so let's go ahead and give this a try now. Oh, so okay, let's just go ahead and remove our debugging statements just to see if it works, and if it doesn't work, we can again go back and start debugging. But not necessary, because it seems it's working. Alright, so there you go. You can see it propagating back and forth, just like the other one. So now, yeah, you could definitely argue that the earlier implementation was much simpler, where we just copy-pasted this for loop and went backwards. But this has a certain elegance. We should probably copy this code over. This has a certain elegance to it, although it does take up more computation time, because you're going to have to reverse an entire array, and that would start to be even worse if the array is larger. But it allows it to be more maintainable, because you're not going to say I want to change something about the properties of this. Maybe I don't want it, or maybe I want it to do delay time +5 or something like that. Then I'd have to do that in 2 places, whereas here I only have to do it in 1 place. So that's the advantage of that. Okay, so that's it. If you can compare it back to the original one that I showed you, which is over here, we still have to add a potentiometer. So let me go ahead and start adding that to the circuit, and then I'll just fast forward doing that. But I'll do a voice overlay talking you through it. So here you see me wiring up the potentiometer. I take 2 terminals and connect them to ground and 5 volts, and the middle terminal is connected to an analog pin, so we can measure the voltage difference. A potentiometer works by outputting a different amount of voltage depending on where the knob is turned. Okay, so you just saw me wire the potentiometer, so let's go ahead and write some code just to test that. Okay, the focus is trying to read the information from the potentiometer. So that's the way we're going to get that information back is through the serial monitor. And what we're going to do is simply, we're just going to take an analog reading, analog read, and right now I'm just going to hard code it, but I will be integrating it properly with the rest of the code. But right now all we want to do is just test to see if we've wired it correctly, essentially. Okay, so this should hopefully print out to the serial monitor. And if we just go and run the code, and then open up the serial monitor, it seems to be working. Okay, so we get to see the values and all the different ranges, that being 0, and all the values in between. This being a simulation, everything is accurate, but of course in real life it would be much messier. Yeah, but that's it, and now we can start working on integrating it into the code. So we're back here in the coding studio, and what we're going to do is we're first going to just declare the pin of the potentiometer, just like anything else, and so that's on pin A2. Rather, that's the value, so I should say pot pin, just for short, A2. Okay, and then you don't need to initialize this as an input. So you can just go ahead and straight away start reading from it. So what we're going to want to do, so let's just save it in a value. So we're going to take the value that this spits out, int value, okay, equal, we don't need to declare it right now because we don't need to define it right now because we're going to be defining it right here. Okay, so val equals analog read, and we're going to say pot pin, because that's the pin we want to read from. Okay, so now that should store a value. Now we need to know what range of values this holds. And I just happen to know that I've looked it up, that it holds values from 0 all the way to 1023. Okay, the comment would actually be that. Okay, so that's the range of values it can have, from 0 to 1023. But I don't want the delay to be an entire second and 23 milliseconds. I want it to be much shorter than that. So let's say I want my delay to be between, let's the original one. So that will be between 0.1 seconds to 0.5 seconds. In other words, 100 milliseconds to 500 milliseconds. And by the way, this is in milliseconds. Okay. So yeah. So how can we convert that? There is a way to do it in code, but the mathematical approach is a little bit easier to understand, and you don't need to have any other prerequisite knowledge. So what we're going to do is we're going to open up calculator really quickly, and we need to get a formula to convert between these two number systems. Okay, so the first thing we want to do is how many numbers are in each range. So in the first range, between 0 to 1023, that's easy. There's 1023 numbers. And the second one, it's a bit different because it's from 100 to 500. So in reality, there's actually 400 numbers in that range of how many possible numbers it could be. So if you take 1023 and divide by 400, not subtract, divide. So now that gives you your conversion factor. Okay, and so if we can just go ahead and think of this. So if you do 1023 divided by a conversion factor, but then you must also add 100. So that gives you your max. So the max of that system is giving the max of this system, and the minimum 0 divided by the same number plus 100 is also giving you the minimum. So notice how the minimum and maximum match up correctly. That means that they're going to match up correctly for every other number in the series, or most likely will. In this case, they will. There might be some cases where they might not. So just because the data that calculator outputs, I'm not going to copy paste this, but instead I'm going to type it out because there have been issues of basically Unicode formatting where it just messes the editor up. So there we go. That's our value. So what we're going to do is let's make another variable, or we can even convert it right here on the spot. We can do divided by. So this is our formula, and just copy this right here. And then we want to add 100 to it. Okay, and then we'll just print this to the serial monitor, just so we know that we're getting the right range of values. Okay, so serial dot print ln, and then we'll just do val. Okay, and we're gonna need to cast this to an integer, just because that division is gonna make it a double or a float. So we're gonna cast it back to an integer. And what we want to do is, if you want to round it properly, there's a technique where you just have to add 0.5, because when converting to an integer, it doesn't actually convert. It just like chops the end off. So if plus 0.5 makes it go to the next, like you could say next ones place, and when it gets the end chopped off, it's gonna have basically converted. But if it doesn't, it's still gonna stay within the correct number. So that's basically how you round in this. The easiest way is just to add 0.5 when converting it to an int, because the ending just gets chopped off. So yeah, let's just take this code. We probably should need to begin the serial.begin at the specified port 9600. It could really be anything, but that's just the standard, and to make sure that things are available on that port. The system is usually available on that port. So let's go ahead and paste that. Hopefully we have no errors, and nope, we do. So the problem is val is not defined. It's because it's called a value. Let's rename it over here, val. And okay, so let's look at our serial monitor. So that looks wrong, first of all. So our numbers are not. So that's 100. We're getting 100, and we're getting 500. All right. Okay, so that is working. That was probably just a little bit of a glitch there. So then we might need to add a little bit of redundancy. Because especially in real life, I don't know why it glitched in the electronics. Most likely, actually, I do know why. Because there's something interesting that happens in programming when you have a value defined but not declared. It just gets an arbitrary memory address, and that memory address corresponds to a number in this case, since we made it an integer. So what we want to do is we should just define like a standard like initial value. So just in case, well, not just in case, when the potentiometer hasn't moved or anything, or we haven't gotten this first reading, we're still going to have some sort of value. It's just a good practice, and in this case, necessary. So now that we know that we're getting the right values, we are going to actually all we need to do is just change delay time to val. And again, if you wanted to do some more redundancy, you can just ensure that if You can add some checks. So if you want to like be for 100% sure, you don't want to get some like weird like in real life an electronic spike or a short to mess anything else with your program. You can add a bit of redundancy. So if you can say if val is greater than 500, which it should never be according to the mathematical formula. Um, oops, I just pasted the entire thing. Then you should say val equals 500. So you're basically just maxing it out. If val is less than 100, forget my brackets. So this is just maxing and like you're kind of capping it at the top and minimizing it at the bottom. Val equals 100. Okay, so there you go. And then you can say val. So now that's going to ensure for 100% sure that you have your values in the correct range, even if the potentiometer somehow gives you a value that's above 1023, which is, remember, what this formula is meant to handle. Okay, so now, again, taking this code, we should be able to now easily change the speed at which our wave is moving, if that didn't happen. Okay, so this code, see, that's one of the disadvantages of doing this, is you have code discrepancies. And that's not how you spell val. You have a discrepancy between what's over here and what's on your other editor sometimes. So, but regardless, we can open up our serial monitor, and we should be able to change this, and by doing so, change the speed. Yep, there you go. So now that this is the slowest it goes, all right, so 0.5, and that would be the fastest, which should be 0.1, so 1 second. Sorry, 0.1 second means 100 milliseconds. Okay, so now if we go ahead and compare it to the original simulation, you can see that we've achieved the same thing. So we've just gone and implemented the same thing. Of course, there's some very minor differences between where the wires are and where the resistors are and everything else, but the effect of the circuit is the same. And that's what's important. So hopefully you learned how to do this, and hopefully you found this demonstration cool. And yeah, see you next time.